Okay, this problem looks at when force is parallel to motion, we're going to be calculating work or anything related to work. So what we have in number one is we have a 7 kilogram ball, and it's rolling on a flat surface with a velocity of 5 meters per second. Okay, then our ball rolls up a hill, and while it's rolling, it slows down. And when the ball reaches a height of 10 meters, it changes direction and begins rolling back down the hill. So the first question is, how much work is done on the ball by gravity when the ball is just rolling along the flat surface? So when the ball is rolling along the flat surface, there is a force of gravity, but if you remember, work is force times displacement. Gravity is pulling down on the ball, but when the ball is rolling on a flat surface, there is no displacement. Okay, so you could do work from gravity is force of gravity is mg delta x, but in this case, delta x is 0, so our work is 0 joules on the flat surface. So if there's no displacement, there's no work. So here it's 0 joules. Okay, how much work is done on the ball by gravity? So again, we're only dealing with gravity right now, between rolling on the flat surface and reaching its peak on the hill. So when it rolls up the hill, it's rolling up to a height of 10 meters. So now we have a displacement. So the work done by gravity is the force of gravity times our displacement. Force of gravity is mg, and so then it would be 7 kilograms, 9.81, and our displacement of 10 meters. So 7 times 9.81 times 10 gives us a work of 687 joules. I'm going to round to the nearest whole number here. And that would be our answer. Now, am I always going to be using gravitational force when I'm calculating work? No. The reason I'm using gravitational force is because the question is asking me to calculate the work done by gravity. Okay, let's look at the next one. A cyclist travels down a flat road at a constant velocity, so that's going to be important, most likely, of 6.7 meters per second. So constant velocity implies that the net force is 0. If we're not accelerating, constant velocity, then our net force is going to be 0 newtons. The drivetrain of a bicycle exerts a 500 Newton force to propel the bike forward. How much work is done by the drivetrain? So how much work done by the drivetrain on the bike and the cyclist if they're riding for 1 minute? Okay, so we know work is force times displacement. So I know the force is 500 newtons, but I don't know the displacement at the moment, but I can figure it out. So they give me a velocity, so v equals 6.7 meters per second. And they also give me how long, so a t or a delta t of 1 minute, so we'll call that 60 seconds because our velocity is in meters per second, so our time needs to be in seconds. And I know that velocity is displacement over time. So if I want to figure out my displacement, I can just plug everything in here. So 6.7 meters per second equals my displacement over 60 seconds. In order to solve for delta x, I would just multiply 60 times 6.7. So we can do that over here. 402 meters. So delta x equals 402 meters. So I can replace that up here. And then all we have to do to find work is force times displacement, which is 500 newtons, times 402 meters. And we get 201,000 joules. So that would be my answer. Okay, these are the questions we did in class for 4.2. Sometimes we're going to see a force on an angle. And so it's going to be important to consider that angle. And if you remember, when we add an angle into the mix, we're using this equation where we have to take the cosine of the angle of the force into account. So with this one, we have a guy pushing a box and it's parallel to the motion. He's pushing with a force of 500 newtons and a displacement of 3 meters. Now, remember, if you're pushing parallel with the motion, then theta equals 0, and cosine of 0 is 1. So work is F cosine theta delta x. So we can do work is 500 cosine of 0 times 3, which would be, so 500 times cosine of 0. Cosine of 0 is 1. So 500 times 1 is 500. And then 500 times 3 is 1,500. So we get 1,500 joules. So when you're pushing parallel to the motion, or the force is parallel to the motion, we can just omit cosine of 0 because you're just multiplying by 1, and that's why where we get work as force times displacement. Okay, a weightlifter is about to lift a barbell with a mass of 120 kilograms to a height of 0.90 meters. How much work will he do on the barbell? So when you're lifting a barbell and you're lifting straight up, you have to overcome the force of gravity. So basically, we need to calculate the work done against gravity. So when we do F delta x, again, when you're lifting straight up, the motion is parallel to the force being applied. So cosine of 0 is 1, so we can just omit that. So what we need to do is, how much does it take to overcome the force of gravity? mg is the force of gravity times the displacement. Our mass is 120 kilograms, 9.81, and 0.90 meters. So the work done is, let's go over here. (1,059 joules). Okay, so now in number 3, the man in the picture below is exerting a force of 250 newtons at an angle of 22 degrees. How much work will he do if he drags the tire 7.82 meters? Here's where we need to use F cosine theta delta x. So work equals, our force is 250 newtons, cosine of 22 times 7.82 meters. So 250 cosine 22 times 7.82, was that what it was? Yes. Gives us 1,813 joules. Again, I'm rounding to the nearest whole number. Okay. This one's a little bit more challenging. We're doing a tug of war between an adult and a child. The child is pulling horizontally from the center of the rope with a force of 30 newtons. The adult, being taller, pulls with 100 Newton force at an 8-degree angle above the horizontal. If each competitor is 1.7 meters from the center, how much work will be done by the adult to win the tug of war? So basically, the adult needs to move the child 1.7 meters. And then what is the net work done on the rope? So let's do the first one. So let's draw the forces here. We're going to do FC for child, and that's 30 newtons. And then the adult is pulling at an angle, so we'll do FA for adult, and that force is 100 newtons. But keep in mind that the adult is pulling at an 8-degree angle. So if I need to just figure out what is the work done by the adult if they're going to win, work is equal to F cosine theta delta x. If I want to know the work of the adult, I need to use the force of the adult. So the work of the adult is 100 cosine 8, and then the displacement to win is 1.7 meters. So the work of the adult is, so 100 cosine 8 times 1.7. 168 joules. Okay, now there are a couple of ways to determine the net work done on the rope. So we found the work done by the adult, so we could do the work done by the child. Now the child is pulling horizontally, so that's a 0-degree angle. So the work of the child, we can just use F delta x because the cosine of 0 is 1. And so I could do 30 newtons times, it would be 1.7 meters. So the work done by the child, is 30 times 1.7. 51. And so the net work would be subtracting, because we're going in opposite directions, the adult minus the child. So 168 minus 51. 117 joules. The other thing you could do is calculate the net force done on the rope, and then and then use that as your force in the F delta x equation. Either one will work. Okay, so remember we said at the beginning of this unit that energy is the capacity to do work. Okay, so one type of energy that we've really focused in on is kinetic energy, which is the energy of motion. If something is moving and it has mass, it has kinetic energy. And so the example I gave here is you have a cue ball, that's the white ball in the pool. And then you have another billiard ball on the table. When you hit the cue ball with the cue, you're doing work on the cue ball. Okay, you're exerting a force over some distance. That's going to give the ball kinetic energy because it's going to have velocity. So when this cue ball is rolling on the table, it has kinetic energy. It has the capacity to do work. So what that means is that if the cue ball hits another ball on the table, it'll exert a force on that ball, which can give the second ball motion. Okay, so when this ball is rolling, it can do work on something else. So it's the capacity to do work. So by exerting a force on the second ball, the cue ball does work on the second ball. So energy is the capacity to do work. Kinetic energy is the energy of motion. So if something is moving, then it has the ability to exert a force on something else and potentially cause it to move. Another example, we said, so you have a nail protruding from a piece of wood and you swing a hammer. When you swing the hammer has a certain velocity. And when it hits the nail, it exerts a force and it can pound the nail into the wood. And so the nail moves a certain distance. Okay, so the hammer does work on the nail. It exerts a force that may cause movement of the object it hits. Okay, so the hammer does work on the nail moves, and thus the nail has kinetic energy for that moment that it's moving. Kinetic energy and work are closely related. So obviously motion can lead to work can lead to motion. So the kinetic energy of a moving object is equal. So this is the important thing. So the kinetic energy of a moving object is equal to the work required to bring an object from a rest to that speed, so whatever speed we're talking about. Kinetic energy can be described with this equation. This is an equation you should know. Okay, it's on your equation sheet, but it should be burned into your brain. Kinetic energy is 1/2 mv squared, mass times velocity squared. Okay, when a car speeds up, you need to do work on the car to give the car kinetic energy. And conversely, when a car slows down, work needs to be done to reduce its kinetic energy. So work is related to kinetic energy in this way. This is another thing that you should know. Work is equal to the change in kinetic energy. So if we take our final kinetic energy minus our initial kinetic energy, that's our change in kinetic energy, that's going to be equal to work. Work is also equal to force times displacement. So these all describe the same thing, and they're all related. This is called work energy theorem. Okay, and this is all based on net work. So you can write the equation this way, where you're looking at 1/2 mv squared final minus 1/2 mv squared initial, and that's going to be equal to our f cosine theta delta x. You can also think about it this way, just knowing that the way you calculate these things is with these equations. Okay, so I'm going to do these homework problems. So here we have an automobile. Sorry about that. We have a car. It has a mass of 1,200 kilograms. It's traveling at 25 meters per second. So first we're being asked, what's its kinetic energy? Kinetic energy is 1/2 mv squared. So all we have to do is plug in the information we have. Mass is 1,200 kilograms. Velocity is 25 meters per second, and the velocity needs to be squared. So if I go over here, I can use 0.5 for 1/2. It was 1,200 kilograms and 25 squared. So 375,000 joules. Okay, what is the net work required to bring it to a stop? So here you need to use work energy theorem. So work is equal to change in kinetic energy, which is EK final minus EK initial. So my car is traveling at a speed of 25 meters per second, and then it needs to stop. So my final kinetic energy is going to be stopped. And if the car is not moving, then the velocity is 0. So if I do EK final equals 1/2, our mass is 1200, and my velocity is 0. 0 squared is 0, and if I multiply all this by 0, I get a final of 0 joules. My EK initial is when I'm traveling at 25 meters per second. So we already calculated that. It's 375,000 joules. So the work required to bring it to a stop is 0 minus 375,000. So the work required to bring it to a stop is negative 375,000 joules. So the whole point of this is you can use work energy theorem to reason through the scenario that's being posed and calculate the work without figuring out you don't have to figure out the force or the displacement, because work is equal to the change in kinetic energy. Okay, here we have a constant net force of 75 newtons. The object is initially at rest, and then the 75 Newton force acts in parallel for 0.6 meters. So the question is, what is the final kinetic energy of the object? Okay, so we know that work is change in kinetic energy, which is EKF minus EK initial. Now, I am initially at rest. Okay, so that means my initial velocity is 0, so my initial kinetic energy is 0 joules. So that means that my work is equal to my final kinetic energy. Now, I'm not given any information about the mass or the velocity of my object, so using 1/2 mv squared isn't going to be useful right now because I don't have that information. But there's another way to write work. Work is force times displacement. I know I don't need to use the cosine because it says it's parallel. The force is parallel to the motion. So I know the force is 75 newtons. And I know that my displacement is 0.6 meters. So my work is 75 times 0.6, 45 joules. And I've already reasoned through it that my work is equal to my final kinetic energy. So my final kinetic energy is 45 joules. Okay, the next question I'm asked, if the object has a mass of 0.2 kilograms, what is its final velocity? Okay, now I can use this equation. So I know that EKF, my final, is 1/2 mv squared. I know that it's 45 joules. And now I'm being told that the mass is 0.2 kilograms. So now all I have to do is algebraically solve for v squared. So we can do 45 divided by 1/2 times 0.2. And that gives us 450. So v squared equals 450. And my velocity equals the square root of 450, which is 21.2 meters per second. So again, work is our change in kinetic energy. Work is also force times distance, and we can relate these things to figure out all of these different parameters that the problems are asking for. Okay, so here we have a 3 gram or 0.003 kilogram bullet. It's traveling at 350 meters per second, hits a tree, and then slows down and penetrates a distance of 0.12 meters. And so the question is, what is the force exerted on the bullet, bringing it to rest? Okay, so the first thing that we need to figure out so I know that work equals force times displacement, and I also know that it's equal to the change in kinetic energy. So initially, we're traveling at 350 meters per second, and then it penetrates to a distance of 12 centimeters, which implies that it stops. So my final velocity is 0, so my EKF is going to be 0 joules. I know the mass of the bullet, and I know the velocity of the bullet, and I know my final kinetic energy. So I can calculate the work. So that's EKF minus EK initial. So the work is 0 minus 1/2 mv initial squared, which is equal to 1/2. I'm just going to erase this to give myself more room. Times 0.003 kilograms times 350 meters per second squared. So we'll go over here and do that. So it's 184 joules. So it would be 0 minus this, so it really would be negative 184 joules, but that negative really is inconsequential. All right, now I'm being asked what is the force exerted on the bullet. So now we can go up and use work equals force times displacement. I know the work is 184 joules, or we could call it negative 184 joules. I don't know the force, but I do know that the bullet penetrated 0.12 meters. So by dividing 184 by 0.12, I get the force. $1,533. So the force is 1,533 newtons. The negative just implies that it's in the opposite direction of where the bullet is traveling. Okay, here we have a baseball with a mass of 0.15 kilograms. It's being thrown straight upward with a velocity of 26.8 meters per second. I'm being asked to determine the work done by gravity, so that's important, by gravity, when the ball reaches its peak. Okay, so work equals force times displacement, but it also equals change in kinetic energy, which is EK final minus EK initial. So my initial is when the ball is thrown. And my final is going to be at the peak. And you should know that at the peak, the velocity is going to be 0 meters per second. So at the peak, my kinetic energy is also going to be 0 joules. When the ball is thrown, it has a velocity of 26.8 meters per second. So we can calculate EK initial. It's 1/2 mv squared, which is 1/2 0.15 times 26.8 meters per second squared. So if we calculate that, we get 53.9 joules. So my work done by gravity is 0 minus 53.9, so the work is negative 53.9 joules. And again, the negative is just saying that energy is leaving the system. So we're getting less and less kinetic energy as we go up. That's it. Just using work energy theorem, what you know about projectile motion. Okay, number 5 here is a little bit more challenging because we have to integrate a lot of concepts, but this is all stuff that you can do. So we have a wagon with a mass of 40 kilograms, and it starts at rest.
For this morning's announcement.
Okay, so we have a mass of 40 kilograms, and we're starting at rest, and then pulling with a force of 90 newtons at a 23.1 degree angle. We're also given the coefficient of kinetic friction, and then we're told that the wagon is pulled for 100 meters. Okay, problem like this, I would always start with a free body diagram, so you know the forces that are acting, because if we want the net work, we need to figure out the net force. Okay, so you know that there's going to be gravitational force. Fg equals mg, which is equal to, we have a mass of 40 kilograms times 9.81, which is 392 newtons. Okay, we know that there's a normal force, but be careful. When we're pulling at an angle, the normal force is not equal to gravitational force. Again, this is when we're pulling at an angle, okay? So I don't know what the normal force is yet. There's a pull force, I'm going to call it Fp, of 90 newtons. And I'm told that it's an angle of 23.1 degrees. And then because I'm given a coefficient of kinetic friction, you can assume that there is frictional force, which we'll call Fk. So to find the net force, or sorry, the net work, I'm going to need to know the net force. Okay. So first thing we're going to need to do is break the pull force into its components. So we have Fpx and Fpy. Fpy is equal to Fp sine theta, and Fpx is Fp cosine theta. And so that's going to be 90 sine 23.1 and 90 cosine 23.1. So 90 sine 23.1 gives me 35.3 newtons. And 90 cosine 23.1 gives me 82.8 newtons. Okay, so I know that my wagon isn't like falling through the ground, and I know it's not blasting off into space. So my the sum of my y forces has to be 0. So I can say Fn plus Fpy plus Fg has to equal 0. And I know that gravitational force is opposite of Fn and Fpy. So there's a couple of different ways you can look at it. You can say Fn plus Fpy has to equal Fg. Okay, either one of these equations will work. Because Fg is going down, it's going to be a negative number. And so when you move it to this side of the equation, you're going to get a positive number. So I'm going to use this one over here. So I don't know Fn, but I know that Fpy is 35.3. And I know that Fg is 392. So Fn is equal to 392 minus 35.3. And that's 357 newtons. Okay. Now, the sum of the forces in the x direction, I don't know yet because I don't know what the frictional force is. I know that Fpx is 82.8, but I don't know what the force of friction is yet. But I can calculate that. So recall, friction, kinetic friction, is the coefficient of friction times the normal force. So Fk equals the coefficient of friction, 0.224. That was given in the problem right here, times the normal force, which we just calculated, that's 357. So Fk, if we just multiply those two together, is 79.96, so I'll call it 80.0 newtons. Now, the sum of the forces in the x direction is just going to be adding Fpx and Fk. Now, Fk is going to the left, so that's going to be negative, so it's going to be 82.8 newtons, which was Fpx, plus a negative 80, so I'm going to do minus 80, and that's going to give me 2.8 newtons. So that's my F net, is 2.8 newtons. Okay, but I'm being asked what's the net work? Well, that's simple enough. I know that I'm pulling for 100 newtons and that my net force is 2.8. So I'll go over here, work equals force times displacement. So 2.8 times 100, which would give me 280 joules. So the net work is 280 joules. Lastly, it asks me for the velocity. Because I'm starting at rest, my initial kinetic energy is 0, and work is going to be final kinetic energy minus initial kinetic energy. If my initial kinetic energy is 0, then work is just equal to my final kinetic energy. So my work is 280 joules, and my final kinetic energy is just going to be 1/2 mv squared. So 1/2 mass is 40, v squared I don't know. So we can just algebraically solve for velocity. I don't have a lot of room here, so I'm going to do 280 divided by 0.5 times 40. And then I'm going to take the square root of that answer. And so my velocity is 3.74 meters per second. Okay, here are some more study guide sample problems. So here I have a ball with a mass of 0.27 kilograms and it's being tossed upward. And they're saying the peak, the height is 5.6 meters. So determine the work done on the ball by gravity between when the ball is tossed and when it reaches its peak. Okay, so we're going to assume that we start at a height of 0, and we're determining the work done by gravity. And because we're being tossed straight up, the angle is 0 relative between the force and the displacement. So work equals force times displacement. In this case, I'm doing gravitational force, so that's mg delta x. The mass of my ball is 0.270. G is 9.81. And my displacement is 5.6. So if we go over here, 0.27 times 9.81 times 5.6 meters gives me 14.8 joules of work. Okay, what is the gravitational potential energy of the ball at its peak? All right, well, this is going to be ironic. So gravitational gravitation. Okay, we're freaking out here. Gravitational potential energy is mgh. So we're actually going to end up doing the same exact calculation. So the work required to lift a ball to a certain height is the gravitational potential energy at that height. Last question is, what is the initial velocity of the ball? So one of the things that I've showed you, and I'll load it up right, and this is in my opinion, the most important concept from this chapter is the law of conservation of energy. The total amount of energy never changes. So when we're dealing with changes in elevation, the potential energy at the top is going to equal the kinetic energy at the bottom. Okay, so see how the gravitational potential energy of this guy at the top here before he jumps is 10,000 joules. When he reaches the bottom, the kinetic energy is 10,000 joules. At any point during his flight or during his fall, the sum of potential and kinetic energy is 10,000. So the sum of potential and kinetic energy isn't changing. It's just in what form does that energy exist? As he falls closer and closer to the ground, he has less potential energy and more kinetic energy. But again, gravitational potential energy at the top is equal to the kinetic energy at the bottom. So that applies to what we're looking at right here. So at the top, when velocity is 0 at the peak, potential energy is 14.8 joules. So at the bottom, the initial kinetic energy can't exceed 14.8 joules. So EK equals 1/2 mv squared. And I know that my kinetic energy at the bottom has to equal my gravitational potential energy at the top. So I can do 14.8 equals 1/2, mass is 0.27, and then v squared. And so we can algebraically solve for velocity. So I'm going to do 14.8 divided by 0.5 times the mass was 0.27. I get 109 point whatever. I'm going to take the square root of that, and I get a velocity of about 10.5 meters per second. So this concept is super important. Energy cannot be created or destroyed. The total amount of energy in a system will not change. So if I have 10,000 joules of potential energy to start, then at any point in time, I can only have 10,000 joules of energy. So the sum of potential energy and kinetic energy is always going to be 10,000. In the case of this problem, if I have 14.8 joules of potential energy when the ball is at its peak, then my kinetic energy cannot exceed that. It has to be 14.8 joules, because when it reaches, or when it starts at a height of 0, then all of the energy is kinetic. All right, let's keep going. All right, a girl pulls a 15 kilogram sled with a force of 37 newtons at an angle of 25 degrees above the horizontal, and I'm given a coefficient of friction. So calculate the force of kinetic friction, and then how much work is done if she pulls for 18 meters. Let's do B first, because that's a one-step thing, okay? I'm being asked, how much work does the girl do by pulling? So I'm only concerned about the pulling force, which is 37 newtons, and I'm told that she pulls for 18 meters. So I'm going to do B first. Work is F cosine theta delta x. If you're wondering, how do I know to use the cosine theta here? Well, I'm being told that we're pulling at an angle. So whenever we're pulling at an angle, then the cosine of theta is not going to be 1. It's going to be the cosine of 25. Okay? So we can plug everything in. 37 cosine 25 times the displacement, which is 18 meters. I get 604 joules. Okay, A is a little bit more complicated, but again, this is doable. This is all stuff that you've done before. Okay, whenever you're dealing with pulling at an angle, I always say, draw a free body diagram. So I'm going to draw my dot. That's going to be the wagon. I know that there's gravitational force. That's going to be m times g. Whoops. And that equals 15 kilograms times 9.81, which is 147 newtons. Okay, I know there's a normal force, but remember, when we're pulling at an angle, Fn is not equal to Fg. When we're pulling at an angle, okay? I'm given a coefficient of kinetic friction, so I know that there's going to be an Fk. Also, I'm being asked what is the force of kinetic friction, and then we're pulling, so I'll do Fp, and that's 37 newtons, and it's at an angle of 25 degrees. Okay, so this is one of those problems where you have to split the pull force into its horizontal and vertical components. So we have Fpx and Fpy. Now I'm only being asked to find the frictional force, okay? And if you recall, the formula for friction, Fk equals coefficient of friction times the normal force. In order to find the normal force, all I need is Fg and Fpy. So I don't even need to do Fpx right now. I know the coefficient of friction, it's given to me. So all I need to do is find the normal force. And we can do that by reasoning through our free body diagram. So I know that Fn plus Fpy plus Fg has to be 0. Otherwise, like the wagon or the sled or whatever's going on here would be falling through the ground or blasting off into space. Okay? And I can calculate, so the other way of writing this is Fn plus Fpy is equal to Fg, because Fg is opposite, so that's going to be a negative. Whoops. But Fg is opposite the other two forces, the Fn and the Fpy. Fpy is equal to Fp times sine of theta. So that's going to be 37 sine 25. Right? Fp is 37, angle is 25. So my Fpy is equal to 15.6 newtons. And then we can go up here and plug everything in. So I don't know Fn, but I know Fpy is 15.6. And I know that Fg is 147. So if I just subtract those, I get my normal force. So 147 minus 15.6 gives me 131.4. So we'll just call it 131. So then I can just go up here and plug that in. So my coefficient of friction is 0.110. My normal force is 131. So Fk is 0.110 times 131 gives me 14.4 newtons. So that would be the answer to A. Okay, here there are multiple ways to do this problem. I'll show you the easier way, or what I think is the easier way. So I have a crash test. A 1,000 kilogram car runs into a wall. It starts with a velocity of 22.4 meters per second. When the car hits the wall, it comes to a stop, and they give you how long it takes to come to a stop. I'm being asked, what is the work done on the car by the wall? Okay, so work is being done because the car is being compressed by 1.2 meters, so that's our displacement, and obviously there is some sort of force being exerted. All right, so we can reason through this. I'm initially going 22.4 meters per second. So that could be my EK initial. And then I come to a stop. That could be my EK final. So work is equal to change in kinetic energy, which is EK final minus EK initial. So EK final, I'm coming to a stop. So that means my velocity is 0. So EK final has to be 0. My initial kinetic energy is 1/2 mv squared. Well, the mass of the car is 1,000 kilograms. And the velocity is 22.4 meters per second. So if we calculate this, 0.5 times 1,000 times 22.4 squared, we get 250,880 joules. For my EK initial. So my work is, again, the negative is less consequential here, but what that's saying is that you have, because you're coming to a stop, you have negative 250,880 joules, so you're losing kinetic energy. But that would be the work done on the car. Easy enough. All right, let's move on. All right. We have a rock with a mass of 0.1 kilograms. and it's dropped from a building that's 15 meters tall. So what I'm being asked to do is calculate the gravitational potential energy, the kinetic energy, and the velocity of the rock at the top of the building at a height of 8 meters and immediately before the rock hits the ground. Okay. So A is asking about the top of the building. So if we're just dropping a rock, we're not like throwing it down, then I know my initial velocity here is 0. And so then I know that my kinetic energy has to be 0 joules. So that's answering right away the kinetic energy and the velocity at the top of the building. The gravitational potential energy is mgh. So the mass of the rock is 0.1. Sorry about that. G is 9.81, and the height is 8 meters. So my gravitational potential energy is 0.1 times 9.8 times 8. I'm sorry, the height of the building is not 8 meters, it's 15. I was looking at the wrong thing. So 15 meters. So 0.1 times 9.8 times 15 is 14.7 joules. Now again, I'm going to go back to this. So my kinetic energy is 0. My potential energy in the problem is 14.7 joules. I cannot at any point have more than 14.7 joules, and the sum of my potential energy and my kinetic energy has to add to 14.7 joules. Okay? Another thing to take note of, the gravitational potential energy at the top has to equal the kinetic energy at the bottom. So what I can do is I can actually skip ahead to C. So I don't know my velocity, but I know that my kinetic energy has to be 14.7 joules at the bottom. Additionally, I know at the bottom my height is 0. So if I plug in a 0 for h, my gravitational potential energy has to be 0 at the bottom. Both of these have to add up to 14.7, which they do. Now my velocity, you can use 14.7 equals 1/2 mv squared. You can also use this formula that we derived from this idea, which is right here. And that's quicker, so that's what I'm going to use. So if you're falling from a height, velocity is the square root of 2gh. So velocity is the square root of 2g, and then the height, or sorry, the change in height is what you're looking at. So it's 2g times 15. So 2 times 9.8 times 15, and then I take the square root of that, and I get my velocity is 17.2 meters per second. You'll get the same answer, and I think I did this on your answer sheet, if you do 14.7 equals 1/2 mv squared. Okay. B, we're being asked the gravitational potential energy, the kinetic energy, and velocity at a height of 8. Okay, so the first thing that I can calculate, if I know the height is 8, is the gravitational potential energy, because that's mgh. So I can do 0.100 times 9.81 times a height of 8. And that's where I'm going to get 0.1 times 9.81 times 8, 7.85 joules. Okay, so like we said, EK plus EG has to add to 14.7. So in order to find EK, all I have to do is take 14.7 and subtract 7.85. So EK equals 14.7, because that's our total, minus 7.85. So I get 6.85 joules. And then if I want to find my velocity, I can use this equation again right here. And again, I'm looking at the change in height for this equation. So v equals the square root of 2g, and then my change in height is 15 minus 8, which is 7. And that's going to give me 11.7 meters per second. You'll get the same thing if you set it up as 6.85, so EK equals 1/2 times 0.100 v squared. I'll just show you that really quick. So I'm going to do 6.85 divided by 1/2 times 0.10. 6.85 divided by 0.5 times 0.1. I'm going to take the square root of that, and I get 11.7 meters per second. So it's the same thing, 11.7 meters per second. Okay, so again, what's really important with a question like this is that the sum of potential and kinetic energy has to be the same throughout the total trajectory of whatever's falling. All right. So last thing. So here we have a block with a mass of 7 kilograms sitting at a height of 4.42 meters, but it's on a ramp. Now that really doesn't matter with all of these energies, but let's just say we have a block, 7 kilograms, and the ramp has a height of 4.42 meters. Okay, the block is released and slides down the ramp. At the bottom of the ramp, it hits a ball, and the ball rolls 10 meters after being hit. What's the velocity of the block immediately before it hits the ball? Okay, so A is simple enough. Again, if we're going from a height and just trying to calculate the velocity, it's just the square root of 2gh. Our change in height from the top to the bottom of the ramp is 4.42 meters. So the square root of 2 times 9.81 times 4.42 is going to be our velocity. And that's going to be 9.31 meters per second. What is the magnitude of the force exerted on the ball by the block if the block comes to a stop after hitting the ball? Okay, so what this is telling me is that EKF is 0, and then this is going to be my velocity for my initial kinetic energy. And so I know that work is equal to my change in kinetic energy, and it's also equal to force times displacement. So if I can calculate the work, I know the displacement is 10 meters, so then I can calculate the force. Okay? So I know that my work is EKF minus EK initial. I know that my final kinetic energy is 0, and my EK initial is going to be 1/2 mv squared. The mass is 7. The velocity is 9.31 squared. And that's going to be equal to 303 joules. The negative isn't really consequential, but we can put it in there because the force is going to be in the negative direction, and it doesn't really matter. Okay, so then I can do work equals force times displacement. I know that my work is 303 joules. We can put the negative on there. Don't know the force, but I know the displacement is 10 meters. So then I can just algebraically solve for that. So 303 divided by 10 gives me 30.3 newtons of force. There's other things you can look at. So my kinetic energy at the bottom should equal my potential energy at the top. So if I do mgh, so 7 times 4.42 times 9.81, I should get something around 303. So we can do 7 times 4.42, whoops. So 7, it was, G is 9.81, and the height was 4.42. I get 303 joules. So it all kind of adds up. All right, that was a lot of examples, and I'm going to stop there, and I'll have this all time-stamped for you.